Hello students, this is question number 1. So we need to calculate magnetic flux, and we know the formula for magnetic flux is we need to do dot product of magnetic field and area, or if we open this dot product we can say it is the magnitude of B multiplied by area and multiplied by cos theta. So we need these three things. So what we have in this question, what is given, let's see. So we have given magnetic field, B is given, and the value is 0.2 Tesla. Area is given, yes, but not directly. It is told that it is a circular loop of radius 0.1 meter. And from there we can calculate the area. So if we have a circle and we know the radius, we can calculate this area by the formula pi r square. So the area of the loop will be pi r square. Now we need to calculate this, which will be pi. You can put the value 3.14 or 22 by 7. That is the value of pi multiplied by r square, which is given in meters, 0.1 meters. We will put that and we'll square it. If you'll use your calculator, you will get value around, I'm just taking the round value of 0.031. The units will be meter square. Remember that. It is area, so the units will be meter square. So we got the second value also. We need to calculate, do some calculation, but we got finally the area. So the value is 0.031 meter square. Let's go ahead. What else? We need this theta also, and that is important. For theta, what information is given? Let's see. So the theta, it is told to us that the magnetic field is perpendicular to the plane of the loop. Remember from which reference the angle is given. Here, the angle with the reference of loop is given. So if you see the diagram, let me try to draw a 3D diagram so that you understand what they are saying. So it is like a circle like this, and this is a 3D figure. And our magnetic field lines are perpendicular to the surface of this loop. So this is the surface. So they are just moving head on. They are hitting them head on at 90 degree. But this is not the theta what I want. The theta should be between B and A. And A is the area vector that we need to draw. So this is how they are. The B is like that, magnetic field is like that, and loop is placed perpendicular. And we have drawn that diagram. So if you draw a area vector for this, which should be perpendicular to this, you will see the area vector and the B vector are in the same direction, or they are parallel. So the theta will be equal to 0. Another way of saying is we can use the formula. If the angle by the loop is given, which is in this case, we can use theta will be equal to 90 minus theta of loop, which is given. So here they have given us the angle. Perpendicular is a fancy word for 90 degree to the plane of the loop. So we will put 90. What is the angle with the loop? 90 minus 90. So it will be 0 degree. So either way, you can understand like this, or you can use this formula. But we got the theta. Theta is 0 degree. Now we just need to use this formula and put the values. So it will be phi, our flux will be 0.2 multiplied by 0.031 multiplied by cos 0 degree. Cos 0 degree is 1. So it'll be only multiplication of 0.2 into 0.031, which will give you value of 0.00 around 6 Webers. So exact answer is 0.00628, but I have taken rounded off values. So this will be my answer. This is the flux going through this circular loop. Let's do the second question here. A square loop is given with side length of 0.5 meters is placed in a magnetic field of strength 0.3 Tesla. The magnetic field is perpendicular to the plane of the loop. So the angle again is given with the loop. Calculate the magnetic flux through the square loop. So we will do what is given. Magnetic field is given. That is given 0.3 Tesla. Area is given, not directly. So what they have given us, the side of a square. So a square will be like something like this. And one of the side is given, which is 0.5 meter. In square, every side is equal. So we can calculate this area. Area of the square will be side square. That is the formula for calculating area of the square. So it will be 0.5 squared. Okay, so the area of the square is just the side square. Side multiplied by side, you can remember like that. So it will be around 0.2 meter square. So now we can put what we have calculated. Area also indirectly it was given, side was given, so we have calculated area now. So 0.25 meter square. Now let's go ahead and think about theta, how it is. It is given, it is perpendicular to the plane of the loop. So this is the plane of the loop. So how they are showing us, how they are telling us to do is like, it is somewhat like in 3D I need to show, somewhat like this. And the magnetic field lines are coming head on. They are hitting the surface at 90 degree. So this is what they are telling us when they are saying that the area is area of the surface of the plane is at 90 degree. And now again the same exercise, we will draw a area vector which is always perpendicular to the surface of the loop. So if this is the surface, I will take this as 90 degree, and when I will find theta is again 0 degree here as in the last question. Or you can use this formula, theta is equal to 90 minus whatever the angle with the loop is given. So you can put 90 here and get 0 value. So theta is also clear. Theta is 0 degree. Let's use our formula for the calculating flux, and that will be, flux will be equal to 0.3 multiplied by 0.25 and multiplied by cos 0. So cos 0 is 1, and if you use your calculator, you will get the value of 0.075 Weber. So that is the answer. Let's go to the next question. So let's do the third question. Let's read the question first. A rectangular loop with the dimensions 0.4 meter multiplied by 0.6 meter. It means the length and width of rectangle is given. Is placed in a magnetic field of strength 0.1 Tesla. The magnetic field is perpendicular to the plane of the loop. Calculate the magnetic flux through the loop. So let's see what is given here. The magnetic field is given, which is 0.1 Tesla. It is given as straightforward. No need to do any calculation, just note down this value. What is the area? Again, they've asked us to calculate the area. So the area, let me use a different color. So it will be like rectangle like this. So the bigger side is 0.6 meter, this side, and 0.4 meter. So this area will be, we just need to multiply these values, length into breadth, which will be, area will be equal to 0.4 multiplied by 0.6, and that will be 0.24 meter square. This is the area, so the units will be 0.24 meter square. Let me note it down here. So the area also, which we needed, we got it. Now let's see the theta. We have to read this line properly. The magnetic field is perpendicular to the plane of the loop. So the angle with the loop is given. So our area vector will be 0 degree again. So if you see, this is the rectangle. Let me use a different color. If this is the rectangle, I'm showing in a 3D, trying to show this rectangle in 3 dimension. So the magnetic field is going like this, perpendicular to the surface. So if we draw the area vector, it will be at the 0 degree or in the same direction of magnetic field. This is A, this is B vector. So theta will be 0. And again, to remind you, we can calculate it by 90 minus theta loop. Put a 90 degree here, you will get 0. So let's go ahead, and we know the third thing, the angle between B and A, that is also known now, which is 0 degree. Now we just need to put values in this equation. BA cos theta 0.1 multiplied by 0.24 and multiplied by cos 0, which is 1. So we can say 0.024. What are the units? They are the capital W with a B, which is Webers. So let's read the fourth question. A circular loop of radius 0.2 meter is placed in a uniform magnetic field of strength 0.5 Tesla. The magnetic field makes an angle of 30 degree with the normal to the plane of the loop. So what does that mean? Normal to the plane of the loop. That means the angle between the area vector and magnetic field is given. So here we don't need to use our formula of theta loop. Directly 30 degree is given. Calculate the magnetic flux through the loop. So let's see. So first, what is given? Magnetic field's magnitude, which is constant at 0.5 Tesla. This is given directly. And then the area is not given directly. They have asked us to calculate actually, because they have given us the radius of the loop. So if this is the loop, this radius is given 0.2 meter. So how to calculate? Again, we will go pi into r square. That is the area formula for calculating the area of the loop. The radius is given, so it will be pi multiplied by 0.2 squared. So that will become around 0.125 meter square. So let me note it down here, 0.125 meter square. And the third thing is important and tricky. So whenever you are calculating and thinking of theta, always if you draw a diagram, then you'll be very easy to understand. So yeah. So now for theta, remember it makes an angle of 30° with the normal to the plane of the loop. What does that mean? See, if it is the magnetic fields are going like that, I will tell you a way to draw the surface, how we can draw 30° easily. So this is the magnetic field. First understand that. Let's assume that magnetic field is going this way. What we will do, we will draw the normal vector because they have told that angle is with the normal to the plane of the loop. So that is what we call area vector. So if the angle is like that, area vector is like that, that is 0°. So let's increase it to 30°. So it will be somewhat like this. Let's say this is 30°. So this is my area vector because normal to the plane of the loop is nothing but area vector. And now if someone says, where is my loop? Can you draw it? Yes, because the area vector is always perpendicular to the surface. So our loop will be like somewhat like this, okay? Somewhat like this. So this is what they want us to think about the angles. And it is very easy. If I directly wanted to draw this loop, I'll be get confused because 30° how it will be. But if I draw the area vector first, then I know my loop will be perpendicular to that and it is easier for me to draw it. So if you want to show it, you can show it like that. Anyway, the angle is directly given 30°, so not a problem. Now let's go ahead and apply this formula. So the magnetic flux will be 0.5 magnitude of B multiplied by area 0.125 and then multiplied by cos. This time it's not 0, it is 30°. So the value will be around 0.054 vapors. So that is your answer. So in this question, what we learned is we have to read these lines carefully. Which angle is given and with what? With the loop or with the normal to the loop? Normal to the loop is the area vector itself. So that it is making angle 30°, the angle will be directly here. We will put theta is equal to 30°. Let's do the next question. So let's read the question number 5. A rectangular loop with the dimension 0.3 meter multiplied by 0.4 meter is placed in a magnetic field of a strength 0.4 Tesla. The magnetic field makes an angle of 60° with the normal to the plane of the loop. Understand? So the 60° is the angle between the area vector and magnetic field. Calculate the magnetic flux through the rectangular loop. So let's do it again. This is the last question. So what will be the flux? We should know this formula. We'll open this. It will be just multiplication of B, magnitudes of A, and then cos theta. So let's see, B is given to us, that is 0.4 Tesla. Uh, the area is not given directly. They have told that it is a rectangle like this, and this is 0.4 meter, and this is 0.3 meter, and this area will be length to breadth. Area will be 0.3 into 0.4, which is 0.12 meter square. So we can get that value, area we calculated. Okay, what about theta now? What about theta? Theta is given 60°. Okay, so let me first understand this problem. So in any question, if you see, we have to just see what is the angle given. So it is given simply with a loop or with the normal to the plane or the area vector. So we need angle between area vector and magnetic field. So that is what it is was. This angle is given with the normal to the plane. Normal to the plane is called the area vector, and that angle itself we will put it here. So let's calculate now. Phi will be, our magnetic field is 0.4, area is 0.12, and then we need to multiply cos 60. What is the value of cos 60? Cos 60 is just half, 0.5, so you can put value here, and then the value will come around 0.024 Weber. So this is the answer for this problem. Thank you. Betaji. Now we will do exercise 1.2. Let's read the first question, question number 1. A rectangular loop of area 0.5 meter square is placed in a magnetic field of strength 0.4 Tesla. Initially, the plane of the loop is perpendicular to the magnetic field. So the normal क्या हो जाएगा 0 degree. The loop is then rotated. So after that rotation happened so that the magnetic field makes an angle of 60 degree with what? With the normal to the loop. So again theta is given. We have to use 60 degree again. Calculate the change in magnetic flux through the loop. So now they are not asking us flux, they are asking what is the change in flux. We show it by delta sign, and that is, you tell me what is the final, and you subtract that from what was the initial condition. You can write it as phi 2 minus phi 1 as you wish. I write it like phi, and at the foot of it I put F letter. So I know that phi final I'm talking about, magnetic flux finally what happened, and then phi I put I at the foot so that I know I'm talking about magnetic flux, what was initially it was. So now actually these are the same questions, but now they are split into two cases. So we have to understand what was happening before and what was happening after. What was happening initially and what happened finally. And then we have to calculate delta phi. So let's just understand this question. So what will be the formula? Formula will be the same. For the flux, we have the formula B dot A, or if I open this dot product, it will be B multiplied by A multiplied by cos theta. So this will still hold. It will be the same formula for both cases. But now see what is happening in this case. So let us discuss what will be the flux initially. So this is my initial, what was happening before. Okay, so for that I need what was the magnetic field, what was the area, and what was the angle. What is this angle? This is what was the angle initially. So I'm just putting another foot I here so that I know I'm talking about the theta initial, so that I can get phi initial. So this is just for small hints which will help me not to get confused when there are multiple fluxes I'm counting. Okay, so what we know here, we know B magnetic field, that is given 0.4 T, and that is constant, so I don't have to change it, right? 0.4. What about area? Area is given. Yes, area of rectangle loop is directly given as 0.5. I will put that value. Easy. And now they're asked, like, initially the plane of the loop is perpendicular to the magnetic field theta, so theta will become 0. So I will put cos 0. So cos 0 is 1, so it will be 0.2 vapors. So this is what I have calculated initially. Let us see what happens afterwards. So I'm calculating now theta phi final. So the formula will be same, magnetic field area multiplication with cos, but the angle is now changed. So I will say theta final we are talking about. So what will be the value of B? It will be the same. It is not changing. Area is also, we are keeping the same, but the angle is changed because loop is then rotated so that the magnetic field makes an angle of 60 degree with what? With the normal of the loop. It means the angle is directly we can put it here as 60 degree. So what is the learning again and again we are getting? If we are saying, if we are given the angle normal to the loop, it means we are getting angle theta directly. So if you calculate this, this will become 0.1 Weber. And now we will calculate what is the delta phi. What is the change in flux? We have to see what is the final 0.1 Weber minus what is the initial 0.2, and that has to come as minus 0.1 Weber. Now some points to be noted here, what this negative sign shows. Okay, we are getting change in flux, but the sign is negative. It simply says that the flux is reduced. Now think about it, about drawing this diagram, so you'll understand what is happening. Initially, let's say the magnetic field is going, we draw the diagram in a different color. Yeah, the magnetic field is going this way. We draw straight lines this way. Okay, and we have a rectangular loop. So I will place a rectangular loop now. Let's say in 3D I want to show, because initially it was at 0 degree, or normal was at 0 degree. So this will be the normal initially at 0 degree, and now they have moved it to 60 degree. So if you want to see the area vector how it will move 60 degree, just see from here the 60 degree will be like this, and now I can create, this will be my future rectangle, how it will look like. This is the diagram we can think of. So initially you can draw area vector. If this is 60 degree, how it will be. And now think about it. If I'm rotating it like this, right? So the flux will reduce. The flux through this rectangle will reduce, and that is why we are getting this value as negative. So even we are calculating, we should understand what actually we are doing. See, the angle was 0, area vector was 0, and then it became 60 degree, then it became 60 degree, and then we are trying to draw a figure so that we understand, oh, it will be tilted so that less flux will be entered. That's why we calculated less flux here. It was more before. So the change is negative. The flux is reducing. So this is the question 1. Let's do the next question. So let us read the question. A circular loop with a radius of 0.2 meter. So here is a circle loop and radius is given 0.2 meter. What we can do, we can straight away calculate the area using the formula pi r square. So it will be pi into 0.2 square, and that will come out to be, let me calculate it, pi multiplied by 0.2 square, that will come out as 0.125. 0.125 meter square. Okay, that is done. So radius is given and we calculated area from it. Now the magnetic field is also given. So B is given as 0.60 Tesla. Area we calculated at 0.125. What else? Let's see. Let's read further. Initially, the loop is oriented such that the magnetic field is parallel to the plane of the loop, and whatever it is, the angle is directly given as theta is equal to 90 degree. So theta initial is 90 degree. Okay. What is about theta final? What is the angle final? The loop is rotated to make an angle of 30 degree with the magnetic field. Now here is the catch. This 30 degree is the angle of the loop, not the angle between area vector and magnetic field, not with the normal. So what will be the theta? Theta will be 60 degree complementary angle. So theta f will be 90 minus 30 is equal to 60 degree. So this was important catch. If you put 30 degrees directly here, you will get the wrong answer. So now let us calculate step by step. What is the initial flux? That will be B into A into 90 degree. And now no need to put values here. See, cos 90 is 0. So whatever it is, it will come as 0. So initial, there is no magnetic flux. So no need to put values here. Okay, we can skip that. So what will be the final flux? So again, we have to use the same formula, BA cos theta. This time it will be final theta. So magnetic field is of 0.6, area is 0.125, and then we have to multiply cos 60 degree. So let me calculate what it comes as. 0.6 multiplied by 0.125 multiplied by cos 60. So that comes at 0.037. So our value is coming 0.037. Can you guess what is the change in flux? That will be final. Remember, first it will be final, and then we'll subtract what is the initial. This time it is just 0. So we can just simply write 0.037 Weber. That is the change. Okay, and it is the change is positive, so the flux has increased. So this is the question answer for question number 2. Let's go for the next question. So this is our question number 3. It says a square loop with side length of 0.4 meter is placed in a magnetic field of 0.5 Tesla. This is given. What else is given? It's a square loop. So we can calculate area of square loop by squaring it, by squaring the side. So it will be 0.4 squared. So it will be 0.16 meter square. Initially, the normal to the loop makes an angle of 45 degrees. See, he is clearly giving that it is with the normal to the loop. That is our area vector. So the theta initial, remember that, was 45 degree. That is there with the magnetic field. The loop is rotated to make the field perpendicular to the loop. Okay, so now the loop is rotated so that it is perpendicular to the loop, or theta became 0, and it is given also here. So if directly given, just put a value. Theta final is 0 degree. Okay, so now if you see, there'll be again increase in flux. We should be able to get positive values. Now how to draw diagrams? Just like seeing this, if you know the angles, this is the magnetic field, and now I'm drawing area vectors. So initially it was 45 degree, at 45 degree, and finally it becomes straighter 0 degree. So our, if you see the square, if you want to see how what happened to the square, so the square was like this, and then the square become straighter like that. So this is a little bit of understanding you should know. So the flux will of course increase. Now let's solve it. So what will be the initial flux? That will be 0.5 magnetic field multiplied by 0.16 multiplied by cos 45, and theta final will be 0.5 into 0.16 multiplied by cos 0. So let me put these values. So 0.5 into 0.16 multiplied by cos 45, or you can take value 0.71. It'll be 0.056, 0.056 Weber, and this will be, where it's gone, yeah, 0.5 into 0.16, which will be equal to 0.08, 0.08, sorry, 0.08 Weber. So what will be the delta phi? Change in flux will be final. Remember that, always confirm whether you are subtracting the right way. Otherwise, in a silly mistake, you will get the wrong answer. So the final has to go first, 0.08, and then we need to subtract the initial one, which is 0.056. So now it will be, let me calculate this, 0.08 minus 0.056. That will be 0.024, 0.024 Weber. This is the change. This much flux has been changed. So at 45 degree, it was some, but when we make it at 0 degree, area vector 0 degree, the more flux will cross, this much will increase. So this is the fourth question, third question answer. And let's see the fourth question now. Let's do question number 4. A rectangular loop of dimension 0.6 into 0.3 meter is placed in a uniform magnetic field of 0.3 Tesla. Initially, the magnetic field is parallel to the plane of the loop, so theta will be 90 degree. The loop is rotated so that the magnetic field is perpendicular to the loop, theta is 0 degree. Directly, our angles are given. Calculate the change in magnetic flux. So let's start. So what we need to calculate is delta phi, and that is delta final minus, phi final minus phi initial. What is the magnetic flux finally, and minus what is the initially. So let us calculate phi I, what is happening initially. So it will be B into A into cos theta, what it was initially. So if you see, initially the angle is 90 degree. So no need to put value even for BA, because this will become cos 90. Whatever values we will put, it will be cos 90, and cos 90 is 0. So initial flux is 0. No need to calculate and put values here. Let's do what will happen to finally B into A into cos theta. What it should be, what is the final angle. So here the magnetic flux, magnetic field is given 0.3, and the area we need to calculate. So it is length into breadth, 0.6 into 0.3. So that will be 0.18. 6 3 is 18. So we can calculate simply like this. And now the final angle is 0. So it will be cos 0, which is just 1. So our value will come as 0.054 Weber. Now what will be the delta phi? Just put the final value first. 0.054 minus initial was just 0. So our magnetic flux will be changed by 0.054. So that is the answer. Now if you want to see the diagrams, let's say magnetic fields are going straight like this from left to right, like this. We have a rectangular loop, and it was initially, the angle was 90 degree, so it must be flat. Its plane should be flat. So it was, we use the color, must be like this, flat. Yeah. So this is the angle, and then it became 0. So actually we turned it like this way. So it became straighter like this. This is the final. That is why we are getting positive value. See, if nothing is written, it means it's positive. So that flux has increased. The delta phi is positive. That's why these values are important, and we should understand what we are doing. And if you see in this case, I will draw parallel vector. First, it was flat, so the angle was 90 degree. That's why it was given 90 degree here. And now the angle is 0 degree. It is in the same direction as in with the magnetic field. So this is what we should understand with this question. Let's go for the final question, question number 5. So let us read it properly. a circular loop with a diameter of 0.5 meter is placed in a magnetic field of 0.8 Tesla. So the magnetic field is given 0.8 Tesla. Initially, the normal to the loop makes an angle of 60 degree. Normal to the loop is nothing but area vector. So area vector theta is given here 60 degree. The loop is rotated. Then what happens? We rotate this loop to make an angle of 90 degree with the magnetic field. Now think about this is theta. No, this is not theta. This is theta loop because it is clearly written the loop is rotated to make an angle. Loop is making an angle of 90 degree. Our theta will be here in this case 90 minus 90, that is 0 degree. So that was one check here. Now it will be very easy to just to calculate and put values. One more thing, it is given the diameter is given to us. So here is a circular loop and the diameter is given of 0.5 meters. So if we want to calculate the radius, we just need to divide 0.5 into half, which will be 0.25 meters. Now we can calculate this area using the circular area formula. So the area will be pi into 0.25 square. It will come around 0.196 meter square. Okay, around this. Okay, now let's proceed. So the magnetic field is 0.8 T. Area we calculated, they given us diameter, we got the radius, and then we used area formula. So it will be 0.196 meters square. That is also good. Now let us see what is the delta phi. So it will be the what is the phi finally, sorry, always final minus initial, phi initial. So let me calculate now what is the initial flux. So it will be what is the magnetic field, what is the area, and then what is the angle. Angle is given 60 degree. I directly put it because the angle was given normal to the loop. And if you calculate this, then 0.078 Webers. And if you calculate final flux, 0.8, 0.196, and now the angle is 0 degree, not the 90 degree, right? Loop is rotated to make an angle of 90 degree with the magnetic field. The theta L is given. So we need to calculate theta, which will become, you can use this formula. Theta will be always 90 minus theta loop. So the loop is making an angle of 90 degree. If we put this, we'll get 0 degree. So cos 0 will be just 1, and 0.8 into 0.196 will come around 0.156 Webers. Now delta phi, change in flux, change in magnetic flux will be final value 0.156 minus what is the initial value 0.078, and that will be equal to 0.078 Weber. So this is our answer for the last question, fifth question for this exercise 1.2. Thank you.